Uh, See, there are two things that I have to point out here. Okay. First, that there has been some miscommunication. I was told that the classes are gone, your classes were gonna start from 27th rather than 20th. So I was under the impression that the first class I would have to take was on 4th, not on 28th. So I right now cannot present anything to you guys. We can have some question and answers. That is fine. I can do that. But right now I cannot present anything to you because again there's a miscommunication that has happened. The content for today's lecture is gonna be put up. Okay, you guys have links for also for people who don't join, because those people also have to watch these live interaction sessions. I am anyways gonna record whatever we are gonna do over these sessions. For the first lecture, uh, I will record it offline when you guys are not there. If you would like, I can share when I would be doing that live interaction session, but not right now because again I'm not prepared. So that is one thing. So you understand, right? So I think Kiran, who had the question, who was the guy who uh, Adarsh? Yeah, wait. So, sir, first problem solving session was not live interaction as per my knowing. Adarsh, can you unmute yourself and tell me what impression you were in?
Sir, in gas dynamics course, in the that course in SOIM NPTEL course in bottom problem solving section one given, sir. But I don't know when
Ah,
the course taken.
that is different, brother.
Problem.
That is different. That is different. That is
So
different.
please conduct in a live
So,
interaction so that we can participate also.
that is a little different. Anyways, so the point was so the thing is that I should have been prepared. I should have prepared for this lecture. The only thing is that I was not informed that the lecture is gonna start today. Okay, so I'll sort things out from the NPTEL side. And the only solution right now I have is I'll record another lecture for you guys, put it up, and you can watch it. Don't worry, we can have the live interaction, whatever is left. I'll take extra time or whatever your questions are, we can do it on 4th. Okay, so that week is also free. Anyways, the first lecture is not very heavy, right? First lecture has to be some introductory. I can even start doing things right now unprepared, but I don't want to do that because first week is very light, right? We'll not be straight away into solving some sessions, as someone pointed out that they would like to have some brief overview also. So I'm gonna do that. So anyways, now let me first start by introducing myself. Okay, so I'll do that. Okay, so hi everyone, I am Shrey Sahai Gupta, and the thing is that I'm a PhD student at IISc Bangalore. Okay, I'm not Shrisha Rao sir's student. I'm one of the students. I'm in the mechanical department. He's in the aerospace department, but I have taken his gas dynamics course. And what else? Okay, so I'm a PhD student and I'm also a PMRF scholar. Okay, so the PMRF scholar is basically, let me see if I can use the pointer. Yeah, so couple of you. So who was the guy who was waiting the longest? Uh, is he available there? Let me see the first message from the chat. Uh, the first message was 1820. I see. I see. Okay. So I didn't know it. Oh, fine. So PMRF is a Prime Minister Research Fellowship. It's a program where PhD students have to do teaching duties, and some of us do it by using NPTEL. Okay. So this gas dynamics course, as you guys would know, this is a recorded lecture. Okay. And we guys, like me for this course, some other student for other courses, take the live interaction sessions for the NPTEL courses. So that is the gist. Okay, that is the idea here, that we PhD students are gonna take your questions and answers. We're gonna try to solve problems and stuff. Okay. Uh, And the thing is that we have to, I can answer that. I can answer that. But okay, so Adarsh has asked about this procedure to enter to the scholarship and stuff. I'll answer that, Adarsh. But just let me complete this slide. Let me get the what clerical stuff first. Okay. So the thing is, in the first first interaction session, I have to properly introduce myself for all of you guys. So I'm Shrey. I'm a PMRF fellow at ISC Bangalore. I'm from Agra, UP, and my bachelor's was from IIT Ropar in 2020. Then after my graduation, I worked in HPCL for a year, for around a year, and then joined here as a PhD student. Okay, you guys can maybe note down or something, or you can drop a message in this chat. This chat is gonna be like active for the entirety of this course, so you can always ping me if you have questions and stuff. I will be very happy to address you guys, and that we can do. Okay. Now, okay, fine. Now, Adarsh, the question you asked. So, Adarsh asked a question: What is the procedure to enter into this scholarship? And he wanted to answer me like he wanted me to answer that. So, Adarsh, that depends itself on who you are and what are you doing. So, this is a scholarship for a PhD students. Okay, and I'm unfortunately uh, unfortunately this fellowship program has now ended, but the thing is that it is gonna start soon. At least that is there in passing news. Okay, so this is gonna start soon, and this is gonna be revamped as a program. Okay, so every year we guys we get some additional what do you call some additional money for doing this additional fellowship for doing this TA-ship. Okay, while doing some research. So this is a fellowship program, and you have to be affiliated in a centrally funded institute, IISc or IITs. There are ICERs also, and you would have to go. You can go on the website. There is this. Maybe I'll share the website. Wait, because I have. I'll share the website. Let me see if that is something. So let me share my screen. Okay. Okay. Fine. So just show it to you guys. You can go to this link. You can go through this website, ask your answer your get your questions answered. There are some institutes you have to be affiliated with. You have to join these institutes. Only then these PMRF things, the procedure starts. You have to get your guide to file a nomination for you. Then they screen it. There is a committee, national committee, which screens all that. That's all clerical thing. So that is something that you would have to do. Okay. Um, what else? So what I'll do is I'll wait for you for someone if they have questions from the first week. Maybe I'll try to answer those questions. Otherwise, we'll end the class today. I'll record a lecture. I'll put it up before the next week. You can go through this that content. You can come back on 4th. We can discuss the next week's content and also whatever was left in this week. Okay. So I think that's it right now because I was not, so people who joined later on, I was not misinformed. I was told that the lectures are gonna these live interaction sessions are gonna start from 27th. Sorry, the lectures are gonna start from 27th. So I was under the impression that my live interaction session is gonna happen from 4th Feb. But turns out that today was the first live interaction session. So I'm not fully prepared to present something to do some questions, some numericals. So I'll do it. Basics. Yeah, I can do that. So Adarsh is asking what are the basics? Okay. So Adarsh, right now I think let's see what material do I have. Uh, basics. So can I ask you a question? If do you want to know what the course is about? Others, can you unmute yourself and like what do you mean exactly
Sir,
by basics? Hmm.
gas
Do you want
dynamics
to
and
get a Mhm.
gas dynamics fundamental and application part. Just in
I see.
week one and week two, briefly and basic part.
So has anyone watched the content? Like I'll do that. I'm just to get a feeler for what other guys are, what page other guys are at. Has anyone watched the week's content? Ah, okay. So let me, yeah, I'll answer these questions. Okay. So nobody, is there no one who has watched the videos, is it? Acha, any one of you got a mail today's meeting? How did you know that you had to attend how you had to join this meeting? Did you get a mail today?
Not today, sir. Before the day before yesterday, I think.
Okay. Which means okay. Yeah. Great. So if that is how I pronounce her name, Afreen, yes. So you've watched the videos. So sir might have gone through the basics, but I'll go through it again. Satvik got the mail last week, so which makes sense, which means that I was supposed to take the lecture today, but I didn't get a mail for me. Like I didn't know. I was under the impression that this is gonna happen later, a week later. But anyways, that can be sorted out, not a big issue. So okay. So let me first start about the what was the idea of gas dynamics? Why do we need to study it? Okay, and why it's uh, guys, you have gone through fluid dynamics, right? Reference book, I'll answer it. I'll answer it, Adarsh. I'll answer. Basically, there is one reference book. Okay, it's the book's name is Modern Compressible Flows by Anderson. I'll type it out. There are other books also. There are some reference books which I am gonna use to solve problems to get a better feel. There are some areas where I feel some books are better, so I'm gonna use those books. But again, reference books is something which I won't be suggesting. It's part of the recorded lectures, so you would have somewhere. Maybe sir will mention the reference book and so on. But I know that there is one famous book which sir is gonna follow heavily. Most of the content is gonna be from that book. So I'll type that out on the chat box. Modern Compressible Flow by Anderson. Let me open that book as well. Let me do that now. So I'll open that book. Okay. So I have a soft copy for that book. It's also freely available. I'm pretty sure about that. But you would have to check that. I'm not uh, very sure.
Yes, sir, available. Sir, another book named
Huh.
Gas Dynamics Volume 1, Murais, J.
Is
Jurko and
this
George of Hoffman and
okay? Can you
Radhakrishnan.
can you type that name? Can you type that name?
Uh,
Hmm. Go ahead, type that name. So I'll share my screen. Wait. Meanwhile, he's typing. I'll share the screen. Okay. We'll go through the index. I see. Fundamental.
sir, these
Zucker.
books are
Yeah,
written in
Zucker is fine.
the
Yeah,
Farsi.
yeah. Great. So these are the books sir mentioned, right?
Sir mentioned. Out of these,
Yeah,
sir,
yeah.
what you referred in your graduation or post graduation
I'll tell you. See, you don't have to worry,
for
okay?
becoming?
All three books, I think most of it is gonna be Anderson. I'll wait. Let me first share my screen. I'll share my screen and then talk. Wait, not like this. I don't want to share the entire screen. I want to share the tab. Wait, stop sharing. So that I guess the thing is that I want to see the screen like you guys also. If I share my screen, then you will see whatever I am seeing. So let me open that book. Wait. So Windows, yeah. Yep. Great. So now you guys are what like looking at this modern income. Let me open the first page. Okay. This is how the book looks. I'll move to the content. Okay. And the question maybe Adarsh only is asking, right? Adarsh is asking. So I'll answer that question also, that which book to follow, what part to follow from which book. Okay. So Adarsh, it depends on how sir is gonna go across this book. There are multiple ways to go through this book. Uh, Okay, but let me first, before answering that question, let me first answer. Let me first discuss what is the overview of this gas dynamic stuff. Okay, so I'll open another book. Uh, and the whole idea of, again, it's not to frighten you all, guys. The idea is to first emphasize the fact that gas dynamics itself is part of fluid dynamics. Okay, it's nothing um, new. Okay, just like how boundary layer is part of fluid dynamics, gas dynamics is also part of uh, this fluid dynamics. Let me just see what. So this is one famous book for wait, not this one, not this edition. Yeah. Okay. So yep. So I'll just show you the content of another book. This is Kundu. Okay. This book is again very famous. Again, no need to look at this book. I'm just trying to emphasize the point that this gas dynamics is in fact a part of this the bigger picture fluid dynamics. See, the contents are here. We have some initial basic chapters, then we go into ideal flows, which are like potential flows, then boundary layer comes, something on turbulence, and you see how aerodynamics is very close to compressible flows. So gas dynamics is compressible flows. Okay, gas dynamics means compressible flows. That is the another name for that topic. Okay, and as I said, just like how boundary layer is part of fluid mechanics, um, uh, gas dynamics is also one. Okay, now the thing is, I don't know, you guys are bachelor students, right? Everyone is a bachelor student. Um, Maybe we can go one round of introduction of everyone. They can tell me where they are from, what is their name, are they working professionals or are they students, and where are they working. We can have one round, right? We are not a lot of people. We're like six. So let's do that.
Good evening, sir.
Good
I am
evening,
Adarsh.
Adarsh. Yeah, go ahead. Hmm.
I am Adarsh Singari from Odisha, Bir Surendra University of Technology. Currently, I am pursuing final year in mechanical engineering department. Last
Hmm.
semester, I took engineering metrology and topped in NPTEL All India rank one in that course. So
Oh my God.
I got offer from
Congratulations.
IIT Kanpur. So currently, I am engaged in uh, 20 weeks internship, winter internship at IIT Kanpur. Meanwhile, these courses I taken because of I did not join in our universities, and I'm interested. I'm not in that much interested in university course. I'm more familiar
Hmm.
with these NPTEL courses, so I planned for credit transfer. So I applied. These courses are beneficial. That's why I took it.
Congratulations, Adarsh, on your internship and the rank. Good. Yeah. So I now understand why do you want to understand the basic, because you have not watched the video, but you would still like
Huh.
to
And sir,
know
I'm
about
not
the
from
course.
aerospace department because this is provided
Ah,
by aerospace. That's why I
actually, the
just
thing is, aerospace again is very closely related, heavily related with
hmm,
mechanical.
mechanical.
So there is no need to worry. 90% of aerospace engineers are mechanical engineers. In fact, I think 100% of them are. I don't know if there are, I don't know, maybe some control engineers or some materials engineers would be there. Well, 90 is not correct then. But again, that does not matter. So again, so maybe Konark or Satvik or Afreen can introduce themselves. We will go one by one. Anyone can just unmute themselves and talk.
Hello, sir. Can you hear me?
Hi, hi. Yeah, I can hear you.
Uh, I am doing second year, sir, in Hindustan University. I'm from Tamil Nadu.
Okay.
Um,
Hindustan University, where is that?
in Chennai, sir.
Okay, great. You're a second year mechanical engineer?
No, sir, aerospace.
Great, great. Good to know you. Great. Maybe other people, someone else, Ram,
Hi, sir. I'm
Sat
Satvik.
Satvik. Yeah,
I'm,
Satvik, maybe you can go ahead. Hmm.
sir, I'm pursuing aeronautical engineering in Satyabama College, and I'm in third year, sir.
Great, great. So we have a mix of second year, third year, and fourth year. Good. Kunak or Ram? Sorry, Ram was there in Ram was there. Hello, Ram, you are not very clear. Maybe you can try to, but you can go ahead, even if it's not clear. Yeah, it's a little unclear. Maybe Ram, you can type your introduction in the chat. That would be great, I guess. No, but anyways, it was nice to hear you. Yeah, it's always better to speak to someone than read, right? So maybe Jayaprakash or Konak, any one of you. It's okay if you don't want to introduce yourself. You can just type that out. So yeah, Jayaprakash.
Yeah.
Hello.
Good evening, others. Good evening, Shay. This is
Hi, good
Jayaprakash.
evening. Yeah.
Uh, I'm actually a scientist in DRDO.
Great. Great.
I actually registered for PhD. I'm doing my
Okay.
PhD with Shrisha Rao sir only. I
Great.
finished my
Amazing.
uh,
Hmm.
first semester. I have finished already. I have finished
Hmm.
my coursework at IIC and came back to join my office. I was there
Okay.
for August to
o-
December. I was there.
Okay.
Mm.
Got
Did
it.
my ME in mechanical engineering from IIC.
Hmm.
I was with Govardhan sir.
Okay. You were
I have
from
done my
Govardhan,
ME
sir.
with
Great.
Govardhan sir. Yeah,
Great.
yeah.
Great. Great.
After
So,
my ME, I joined DRDO,
okay.
and now now I have joined as a ERP student with Shirisha Rao.
Amazing. Amazing.
And
So,
sir,
you know that.
sir has,
Go. Sir has told you to
yeah, yeah,
attend this.
yeah. I don't have any leaves. That's why I have taken
Hmm.
this course from NPTL. Sir has
Amazing.
suggested. Mm,
Amazing. Amazing.
yeah,
So, because we know, like I know Govardhan sir, and I also know Shrisa sir.
yeah, yeah,
There is a Jayaprakash now in
yeah,
Govardhan sir's lab and ISER
yeah.
lab.
Early.
You have met him, is it?
Okay.
Uh,
No,
there's a
I
sub.
have met this. I just met this while I was joining, but
Okay, okay.
I did my ME long before.
Okay, okay. Which is understandable.
Yeah.
Yeah. But nice to meet you. It's good
Yes,
that we
yes.
have like
Mm.
a very
Yeah,
this very what do you call very diverse group of people attending this course. Did you watch the first week's lecture? Like I think maybe I can call you
yes,
sir or
yes.
something because yeah. So you watched
Not
the
a
lecture.
problem. You can call by name also, not a problem.
Yeah,
But
yeah. It's
yeah,
okay.
I have gone through the video lectures, right?
Hmm.
Uh,
Okay. So would you
this
like
was
to tell?
introduction.
Would you like to just briefly, like within, like with in two lines or three, do you want to tell what did you understand? What was the overview of the course? Or did sir get into the details already? I think not, right?
No, sir has covered the introduction, what is gas
Hmm.
dynamics, and after that, sir has given the introduction of to thermodynamics. Sir has given thermodynamics introduction in two lectures,
Okay. So
and he
there are
has
only.
solved.
th-
Mm,
Uh, no, go ahead. Sorry.
yeah, and sir has solved few problems in this
Okay.
related to thermodynamic relations, isentropic flows.
Hmm. Okay. Okay.
Yeah.
But these are like so the sir has taken already how many lectures? Is it? Let me check. I'll also check.
Second week, videos have already been released.
Oh, that is fine. But in the first, so this I don't know if you were there already. I was not informed
Yes, sir.
that today was the first session. So I have not prepared properly
Yeah,
for
yeah,
this lecture. So I'll just check how much has he taught. Gasdynamics.
10
What is
videos, sir.
this? Yeah. So yep. Let me see what is the first week's thing. Yeah. So 4, 5. Yeah, 4, 5 only, which is okay. This is the one, right? This is the video lectures you're watching, or there's a different one. Let me check. Could be this one also. No, no, not this one. Okay, fine. So let me go back. Uh, yeah. So even like how just Jayaprakash told me, I could just now recall what all sir would have taught. So it's fine. The first week's content is pretty basic. Okay, the second week's content, for the second week's content, we are going to discuss it on 4th. So that is no problem. When today is not for the week 2. Okay, Konak, maybe you're the last guy, so you can introduce yourself and then we can go ahead, maybe talk a little bit about the course, what maybe answer Adarsh's question and close. Maybe Konak is maybe if you would like, you can introduce yourself in the chat. Ram, you could also introduce yourself in the chat. I didn't get your introduction. There is someone else in the lobby. So hi, Umar I don't know how to pronounce her name. Would you like to introduce yourself? Sorry, I don't know how to pronounce her name. Maybe Patil is a right pronunciation.
Yes, 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 sir.
So do we call you Patil?
Yes, yes, sir.
Okay. Would you like to introduce yourself?
Yes, sir. My name is Umer Pasha Patil, and I'm from Sanjay Godat University, Kolhapur, studying in third year BTech. You're not
Great.
audible.
Umair Pasha. Okay, that's how I pronounce the name. Great. Great.
I'm
So,
audible, sir.
you are audible. Am I not audible enough?
I just came by Bangalore, sir, from
Okay.
internship.
Okay. Okay, I see. So
Okay.
Konark has also introduced himself. Uh, his mic is not available, so that's okay. Okay, fine. And Ramchandra is there, who is from Rajalakshmi Engineering College, and he would like to learn about the compressible flow. Okay, great. So, okay, great. So let me just okay, let's discuss this one thing. Let's try to discuss why sir started with thermodynamics. Okay, why do thermodynamics enter the picture when we are looking at gas dynamics? What is going on? Okay, so okay, and before that, let's just discuss what are the brief contents that you're gonna look at um, in gas dynamics. So first of all, this chapter 1 again is a very brief introduction that we'll not look at. We'll look at the conservation equations. We'll need some governing equations in our gas dynamics course. Primarily, we'll be solving 4 equations to be precise. To be precise, there are 4 equations. Okay, can someone just simply tell what are the 4 equations that we are gonna deal with? You guys can see my screen, right? Most of you could just simply read 3 of them from the screen itself, but yeah.
Continuity or conservation of mass, momentum
Uh-huh.
equation, which is known well known Navier-Stokes equation in three dimensional coordinates,
Great,
and
great.
energy equation, conservation of energy principle.
But these are only 3. Can someone tell me which is the 4th equation am I talking about? Or do we not need to solve? Am I being wrong? I can be wrong. That is also true.
Hydrostatic
Ram, which one?
equation of states.
Good, great. So yes, equation of
equation of
states. Great, great. So there is some lag. I cannot figure out who is speaking, but I could see Ram's said equation of state, which is amazing. And that is why, see, in fluid mechanics, say in viscid flow, say Bernoulli equation, right? Or um, some Navier-Stokes equation, for example, or some what else? Boundary layer theory. We don't start with thermodynamics there as well, because in principle, in the regime where the gas dynamics is like in the regime of gas dynamics, there is a heavy coupling between the momentum equation and energy equation. Okay, and so it turns out that this coupling is like this is one of the salient feature of gas dynamics, that there will be heavy coupling between the energy equation and the momentum equation. See, momentum equation and continuity equation always have a coupling. Okay, and in certain cases, we can even go ahead and ignore momentum equation. Do you guys know what case is it possible to what in under what conditions there is a very simple solution to the Navier-Stokes equation? Do we always solve Navier-Stokes equation? Like, do you guys know an example where we just simply do not solve Navier-Stokes? We go ahead with some other like some other simpler form of Navier-Stokes.
Sir, ideal flows, we use Euler equation. Neglect the viscous
Amazing.
effect.
Yes, but suppose so great. That's true. That's true. In fact, that reminds me, in aerodynamics, we always deal with this 1D, not 1D, sorry, Euler equation. We always go and solve, we don't solve the Navier-Stokes, we solve the Euler equation. That's true. Suppose there is viscosity. Are there some cases where viscosity is still important, but still we are not solving any momentum equation? Like no Navier-Stokes equation. We will have to solve momentum equation, but a very simpler form of momentum equation. So maybe let me write this down. Okay, so this would require me to start. Okay, wait. So let me create a PPT for you guys. Sorry, I was not prepared today. I'm just. I think just
Fine.
have to.
Fine.
Yeah. So April 2025. Let's start. Let's start with a PPT. Let's start these things. This could be one good introduction. So maybe we'll continue. So we have lecture one. Let's see. Okay, I'll share that PPT. Okay, now. So give me a second. Lecture one. Great. Let's present. Okay. I'll share my screen now. So I've created a PPT. Now we'll discuss. You're able to see my blank screen?
Yes, sir.
I
Yes,
guess.
sir.
I guess. Great. So the question, let me just type down the question. What is the question? Are there cases where the momentum equation is solution to momentum equation is straightforward? This is the question. Sorry for some of the people who feel this is uh, like it's very primitive for the lecture one, but seeing the variation in the course, we will have to start from the very basics, very simple discussions. So sorry if someone feels it's very repetitive and very primitive, the discussion we are having. Excuse me for that. Okay, so this is one question. The second thing is that I'm saying that gas dynamics, uh, in the regime of gas dynamics, the energy equation and the momentum equation is heavily coupled. Okay, so this is the question number This is a statement. Okay, this is the statement that I'm making. Okay, but the underlying question to this was, why did sir start with thermodynamics? One very simple answer to that could be that thermodynamics is very basic and you require knowledge of thermodynamics to start with anything, even with fluid dynamics. Even if I share my screen and show that book on fluid dynamics, the first chapter will have a refresher on thermodynamics. So that is one primitive answer, very trivial answer, that thermodynamics is the very first thing that you have to solve. Okay, you need to know how uh, okay, so thermodynamics is something that you need to know a priori to go on with other things. That is one thing. But is there a special reason of why gas dynamics, which is an advanced course, a relatively advanced course, why that requires a refresher to thermodynamics? I'm pretty sure no course on boundary layer theory requires a refresher on thermodynamics. Nobody starts with that. I'm pretty sure. So there is a reason, and I'm telling you that the reason is in the regime of gas dynamics, the energy equation and the momentum equation are heavily coupled. Okay. Now, what does that mean? What do you mean by heavily coupled? That is one thing. Okay. So let me point that I'm asking questions on your behalf. You can go ahead and stop me and ask your own questions. Okay. What is this? Okay. Okay. Then I'll ask another question. Are there cases outside of regime of gas dynamics that are still uh, that exhibit heavy coupling between between the energy and momentum equation. Okay, so this is one question. Now, while writing this question itself, I thought, what is this regime of gas dynamics? What do you mean? I never started with that. Okay, so let me first tell you guys what is this regime. Okay, so every one of you knows that everyone. Wait, someone has joined. Let me just put them in. Okay, so every one of you knows that something about Mach number is gonna come very soon, right? Guys, maybe someone can volunteer and just answer. Okay, that would be very nice. I would get a lot of motivation to talk, right? It becomes a dialogue and it becomes very easy
Yes,
for
sir.
me,
Yes, sir.
right?
Make one.
So, right, Mark number is gonna come very soon. Okay, and we also know that there is, and we saw that the book's name is Modern Compressible Flow. In the chapter's name was Compressible Flow. We are seeing that compressibility has to play a role. And we know that as soon as Mach numbers enters the picture, if it's higher than certain value, compressible effects are gonna show. Okay. Now, what do you mean by compressible effects? What is compressible effects? Do you do you guys know any? Okay. And also, the book's name was Modern Compressible Flows, I guess. It was not Modern Compressible Fluids. That is again another interesting aspect of gas dynamics. I'll talk about it. Um, and the best I the on the top of my head, the best example I have for you guys to appreciate what compressible flows are, what gas dynamics is I'll show it to you. Okay, so where is this PPT? Wait. So I'll write another question for you. Okay, and you have to answer that question now. Okay, so I said that Mach number is gonna enter the picture very soon. Okay, that was one thing which I said. Then I said the chapter's name, chapter slash books name says compressible flow. Okay, compressible. Okay, that is the one thing. And again, the third question is it says compressible flow, not compressible fluid. Okay, compressible flow and not compressible fluid. The book's name, the reference is book's name. Okay, and the last question: does it matter? Does it matter? Okay, so maybe any one of you, would you like to volunteer a dialogue? I will ask you question. You would have to answer it. On top of, nothing is right and wrong. You can just I want to have a interaction with someone. Any one of you can just volunteer, unmute themselves. No? Should I go ahead?
Yes, sir. Sir, Mach number plays a vital role by deciding the sonic flow or subsonic or supersonic, hypersonic pressure.
Okay.
Second,
Hmm.
compressible means if a fluid changes its density by applying some pressure more than 5%, then it is called as a compressible flow.
Wait. Let me write these things down. You're saying very good things. Density changes greater than 5%. Greater than
5%,
5%. Then
5%.
you also mentioned that sonic, hypersonic, hypersonic,
Supersonic, transonic.
su- supersonic and stuff. Okay. So these were
uh,
the two things that you said, right? So again, I'll again ask questions. Very stupid way of introducing anything. But yeah, again, some questions. So does it mean that whenever I say gas dynamics, does it always have to be related with sonic, hypersonic, and super? And at least I know, at least now I know that you all have this pretense. You all know that gas dynamics has to do with sonic flows, supersonic flows, hypersonic flows, maybe subsonic flows. So now you guys know that in the regime, the gas dynamics regime, when I bolted this out, I never explained this out to you, but others explained it for me. Does this mean, asking this question, does this mean that velocities are going to be in the order of the sound speed? Okay. Is this what this means? Uh, Wait. A is the sound speed.
Yes, sir.
Does this always mean that? Okay, this is order. Okay, this is order basically means that these will be comparable values. If speed of sound is
Or
340 meters per second,
or
then
or
you will
sir,
be 100. Hmm.
the ratio of the kinetic energy here, you represent the kinetic energy term, somewhere kinetic
Yes.
energy, and A represent
Yes.
somewhere internal, sorry, enthalpy term. So it
I
is the
see. This is also interesting. A
ratio of
is enthalpy, and
and
U is So it's very
this is
interesting how.
not that direct related to not we can say A is equal to
No,
enthalpy, but it the
Adarsh, I'll tell
ratio.
you. You have pinched a very interesting nerve. Very important point. What you're basically talking about is this is a non-dimensional term which is called. Let me remember it. What is it called? Is it called Euler number? No, it's not called Euler number. What is it called? This is what is this number? So that let me check. I have forgotten. Let me check. I'll tell you. Very interesting point that you have raised. Let me check. So I know that this is a number with this is a
Knudsen number.
non-dimensional number. Which one? Which one?
Knudsen number.
Knudsen. No.
हाँ,
Knudsen number is Knudsen number is again very interesting. Okay, let me write that also down. But before, just let me check what I was looking for that in that book. Yeah, okay, got it. I had forgotten the name of that term. I'll talk about it. And this guy told about Knudsen number. Knudsen number. So again, now you see, just by discussion, we are able to grasp what all things we are going to look at in this course. Knudsen number is again something that we look at. Very interesting. This is called Eckert number. What does this mean? We'll look at it. Okay, very interesting. This guy mentions that gas dynamics has to do something with Eckert number, and that is totally accurate. Totally accurate. Eckert number only comes into play is again just like how Mach number is important in compressible flow. Eckert number is also important in compressible flow, and we can show that this whatever this guy told me Eckert number. I'll first define what Eckert number is, which is, again, right now you don't need to know what this Eckert number is, but I'll just go ahead and define it for you. It is Cp delta T force, delta T what? Some characteristic delta T ref. Let me say delta T ref. This is the Eckert number, kinetic energy upon enthalpy. You see, right? Just how he mentioned enthalpy and kinetic energy. Eckert number is defined by this. And it turns out that it is proportional to Mach number raised to the power 2, square of Mach number. So you see, in gas dynamics, you have kinetic energy coming in, you have enthalpy also coming in. Now, how does enthalpy come in is something that we'll have to see. This is also one question. Is enthalpy coming into the picture? Does enthalpy come into the picture? It does. We'll see that. Not today, but we'll see how enthalpy comes into the picture. But the whole point of this was okay, so there are some things that we have answered. I've answered the question that regime of gas dynamics is what we know. We're getting a little bit of just that gas dynamics has to do with something of sonic and supersonic. Then density changes have to be greater than 5%. Something we have not talked about. I'll talk about this as well. Then what else? What else have I not talked about? We have not talked about the heavy coupling. Okay, so heavy coupling can be answered by this fact. This equation. You see, I'm saying just take it at the face value. I'm saying that for compressible flows or in the regime of gas dynamics, Eckert number is not zero. It is some value. Okay, it is of the order of 1. Let's say it's 1, which means that kinetic energy is proportional to your is comparable to your enthalpy. You remember in thermodynamics, if you would remember, just loosely you remember, a lot of time in thermodynamics we'll neglect kinetic energies and potential energies, right? But it turns out, eh, does anyone remember this assumption from thermodynamics? Maybe someone from second year can tell. Afrin, would you like to tell me if you have come across this assumption on thermodynamics? Second year people know about thermodynamics a lot, so let me ask. Maybe someone else who would like to just answer. Okay, so I'll just take it right now. We don't want to continue this thing. I'll just tell you that this is a very common assumption in thermodynamics, that we neglect kinetic energy in with respect to this static enthalpy, or let's say enthalpy right now. We neglect kinetic and potential energies. And in gas dynamics, we can't do that. That is the very first thing that happens in gas dynamics. Even in the first few lectures, you will go ahead and you will see that there is a direct balance between your enthalpy and kinetic change in enthalpy and change in kinetic energy. So Eckert number is going to play a big role there. Again, you won't see Eckert number coming in entirety of your course. You won't see mention of it, but we'll see. If I'll try to present something or discuss it. How does this enter? Why is it a non-dimensional number and so on? We'll see. Acha, also, can someone check if this is non-dimensional or not? Have I written it as a dimensional quantity? Is this okay? Whatever I have written down. Just someone check and let me know.
Cp delta T whole square. Above is the internal energy.
No, U is okay. Sorry, my mistake. Let's keep velocity as V rather than U.
Specific kinetic energy.
Yeah, specific kinetic energy. Yes. Okay, so I think this is non-dimensional. Someone can just check and let me know. Okay. So density changes greater than 5%. We have not discussed. I'll discuss that. We have discussed regime of fluid gas dynamics. We've discussed this part. We have not discussed Knudsen number. Mach number is going to enter this picture. This is fine. We have not discussed heavily coupled. Heavily coupled also is something that we have to discuss, but we have briefly, like, we have discussed it slightly here. We see that why, okay, now why, okay, so one way to understand why there's a heavy coupling between the momentum equation and energy equation is that momentum equation has something to do with kinetic energy. Energy equation has to do something with the enthalpy. So that is why there is a heavy coupling. This is a loose answer. I can actually show you how this happens. More precise answer, more technically um, precise answer. We can see how that coupling happens. Okay, that is something that we have to discuss. One thing which I am looking forward to discuss with you guys is this question. Okay, and also this. Come back. Let's come back to the very initial question I was interested, like I wanted to discuss. This is very interesting actually. This is something I wanted to answer. So maybe someone else from others, but not if not, then maybe our others can comment on these. The second question. Let's keep the first question, the first bolded question away. The second question. Can you? And he mentioned this. Let me point that out. he mentioned he mentioned Euler equation in ideal flows. Does any one of you feel that we are discussing something that they are not familiar with? Please let me know. Very, very important for me. Please let me know if you think you don't know about Euler equation, you don't know about ideal flow, you don't know about any of the word on the slide. Please let me know. Okay, I'll assume that everyone knows about Euler equation and ideal flows. Maybe not the second yearites or third yearites. Euler equation is a little bit not how fluid mechanics is taught in bachelor's. But if you don't understand, either don't hesitate, or if you're hesitating, don't worry. Don't worry about this thing. This is not important in this course. Okay, maybe. Maybe it's a little important. Towards the end, we'll see if Euler, we actually, whatever we'll get, Euler equation is something that you'll derive very soon. But again, you don't require Euler equation and ideal flows very soon right now. So let's drop that. So don't either don't hesitate or don't worry. Okay, that's my thing. I just wanted to point that out. Uh, Whatever is important, we're gonna discuss. Okay. So maybe others, because nobody else has volunteered. Maybe you can tell me what do you think about the second question. Are there other cases where momentum equation is just straightforward, the solution to it? I'll write something maybe. Let's move ahead with the discussion.
Maybe where the heat transfer is.
Hi, yeah. I was waiting for you to comment. Yeah, like talk. Hi, yes. What were
Yeah,
you
yeah.
saying?
Wherever the temperature effects are, wherever the
R.
temperature effects are more,
Uh-huh.
or more, where the temperature, maybe heat transfer or something, instead
Amazing.
of having
Great.
a
Great.
hypersonic flow or
Great.
supersonic flow, where the temperature gradients are very high, then
Great.
we'll be using this energy equation is coupled with the momentum equations. And
Amazing. This is exactly what I was looking for. Great.
maybe in the
Hmm.
boundary layer, what about the boundary layer during ablation or phase
During
changes?
phase changes.
During
You
phase
said you
change,
mentioned you
uh,
you mentioned ablation. Did you say ablation? Boundary there also you said.
ablations during
What are
yeah, yeah.
what are ablations?
Phase,
I am not very sure of that term.
be evaporated
Evaporation, basically.
to
I see.
atmosphere.
Ablation.
We
Got
can
it. Got
see
it.
because of the heat
You mean
transfer,
I got it.
the solid
Ablation.
is
I got
directly
it. Got it.
evaporated. I mean, the phase
Okay. Got it. What do you
uh,
mean? I got it.
it
Ablation
absorbs the
in that one.
heat. Yeah,
Hmm. Okay. Got it. Got it.
but
Great. This is exactly.
that is also
Hmm.
hypersonic flow only.
True. 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 But there is actually not directly related. There are these you know in my bachelor's I worked on microwave ablation of cancer tissues. So I
Okay.
thought some ablation from that sense, but again heat transfer, basically some evaporation is
Yeah.
happening. So, and you're talking about hypersonic flows where ablation is happening because of high temperature, but this is exactly what I was looking for. So interesting. Boundary layers, right? Boundary layers does involve some coupling, but that is specifically under the regime of gas dynamics. So
Yes,
these are
yes.
called compressible boundary layers. In incompressible boundary layers, you won't have any coupling. We don't look at it. Okay. So compressible boundary layers.
Sir,
In
in
phase change. Mhm.
incompressible flow, the coupling between continuity and momentum.
Yeah. So that was my point. My point was that generally speaking, in a larger on a larger scale, momentum and continuity are always coupled. Always coupled. Okay, maybe let me use the next slide. Too much on this slide. Okay, I'll come back to that slide. There are a few things which are left on that slide itself. The major point I was trying to emphasize was momentum and continuity are always coupled in any general flow. It cannot happen that these two are not coupled. You can't find any non-coupling there. Is okay. Let me see. Maybe let me see. Are there decoupled? Is there any decoupling between momentum and continuity? Is it possible?
No, they are always conserved for any flow.
Yeah, they are conserved. But the question is, can they be decoupled? Well, it's a quite a stupid, trivial question because both the equations have rho and u in them. So maybe coupling is not involved. There is one case. Yeah, wait, I remembered one case. Can momentum and continuity be decoupled? Think of there uh, well, loosely speaking only, again, very loosely speaking, they are decoupled in one case. I can remember one case. So think about it. Maybe there is one case. But generally speaking, they are always coupled. Again,
For
uh,
incompressible flows.
so you're saying incompressible flows here, is it? Wait. So in an incompressible flows, to answer that question, let's not write it here. In incompressible flows, generally you will have momentum and continuity always conserved. Think about ideal flows. Okay. Think about uh, what would you like to think about? Say Bernoulli only, right? So suppose your tank. Take a take example of take example of uh, emptying tank, a tank that is getting emptied. Okay, the flow rate gets decided by the uh, s- static pressure. Okay, sorry, this there's a relation between pressure and velocity, right? Velocity is related with the mass flow rate. So you see, continuity is always like when you solve for this emptying of the tank, you solve for mass conservation and you also solve for momentum conservation. That is, momentum conservation is basically Bernoulli. Okay, that is how you find the mass flow rate through this tank. Okay, when you write, you are actually solving for velocity and density. So they are in generally coupled, but I can think of one case where it can be called decoupled. Not they can never be decoupled, but loosely speaking, if we want to um, uh, we want to beautify our discussion, we may, but they're not technically decoupled. They can never be. In fact, energy, momentum, and continuity, they can never be coupled and decoupled. Precisely speaking, even in incompressible flows, energy equation is still coupled, but it does not matter. That coupling does not matter. That is the thing. So that is what I meant. That is what I mean to say. Does the coupling between these several equations matter in certain cases or not? And my claim is that in gas dynamics, energy and momentum equations are generally are will be coupled. They cannot be decoupled. That is the whole point. That is the overview of gas dynamics. Okay. Okay. So let me write that down. Are coupled energy and momentum equations are coupled in gas dynamic regime. Okay, so anyways, now okay, let me discuss just this one case which I just wanted to tell you guys, and this is exactly what Jay Prakash also mentioned. Sorry. Consider a pipe flow. Okay. For a pipe flow, can you guys, can any one of you tell me? So let me write this down. This is exact pipe flow. Okay. This is something that we're discussing in like independently again. We'll come back to what are these open-ended loose ends, but I'll come back to everything. We'll close it. But for a pipe flow, what is the energy? This momentum equation and continuity equation. Any one of you?
Rho AV.
Interesting. Very interesting. Nice. Rho AV equals to constant. This is the momentum. This is the continuity equation. Great. I think what's your name? Afreen. Yeah. Great. Afreen, can you tell me also the momentum equation? Let me just bring the accuracy. Yep. So no. So let me just write it down. This is the energy. This is the momentum equation. If you will solve for pipe flow, you will get this momentum equation. This is the momentum equation for a pipe flow. That the pressure drop across this pipe is gonna be half this FL by D rho V square. This is basically the mood. This is coming from the Darcy friction coefficient. This is the Darcy-Weber friction coefficient. This is the definition of that coefficient. And if we know this coefficient, we simply write the pressure drop across the pipe is gonna be of this form. Okay. In engineering applications, for a pipe, because you have documented friction factors, you have this factor F documented, you don't solve for momentum equation. You simply say that if the pressure at the inlet is known, you can know the outlet pressure. Okay, again, I am speaking very loosely here. I'm not mentioning under what cases this is exactly true. There will be some cases where this can go wrong. Okay, so I've not even started a discussion on laminar turbulent. So there are a lot of details here, but loosely speaking, we can write momentum equation as delta P equals to FL by D rho V square by 2. Does someone have a problem with that? Does someone not understand how does this come? Why is this momentum equation? Why does someone have this question? I want to answer that question. Please let me know if you have this question. If not, then we'll move ahead because I think there are a lot of loose ends that I have not answered. Then it becomes just confusing. What am I saying? There is no flow right now. So let's not just randomly discuss few things. Okay, so this is a momentum equation. We'll assume we'll say that we know this. Okay, you can actually go and see that this is the momentum equation for a pipe flow. Okay, now given that, you see in principle these two are in principle again, not in principle. Loosely speaking, they are two unrelated. Okay, how are they unrelated? Uh, Unrelated by this F maybe. You see that unless you know, unless you can have any flow rate for the same pressure drop in principle, if you can change your A or something, you see that they are not decoupled as such. Again, if you change the flow rate, you will have a different pressure drop, but at least there is no direct coupling. You can solve one without solving the other, right? If you're given the flow rate, you can solve for the velocity, or given the pressure drop, you can solve for velocity and density. You don't need to solve them simultaneously. That you can't do in energy, in gas dynamics. You have to solve them simultaneously. They're coupled. There are terms which will affect the other equation, and there are terms which will affect the other equation. There is heavy coupling there. That is what I meant to say. Generally, these two equations are always coupled. You can see even in this case, it is coupled. So in principle, you can't say that it is decoupled. Okay. Just let me see. I'm getting some message. Okay. Fine. Okay, so that is the first thing. Then I asked him a question. I'll go back to the previous slide. The last discussion I had with Jay Prakash was about this. Are there cases outside of regime of gas dynamics that exhibit heavy coupling between the energy and momentum equation? And he mentioned temperature gradients. He also mentioned heat exchangers. You see, uh, uh, suppose there is a water heater. Okay, and water heater is like, so suppose the geometry is of such sort that there's a pipe and you have a heating coil outside of the pipe, and you are pushing in water at say 15 degrees Celsius, and you're getting water out at the out uh, at 100 degrees Celsius. You're getting steam out of it. Some steam you're getting. Now tell me, are there going to be density difference greater than 5% or not? That is the question I wanted to ask. Maybe any one of you can let me know, in a heat exchanger problem, are there density variations? Are there significant density variations or not?
There
Uh,
will be.
there will be. But is a heat
Yes.
exchanger problem a gas dynamics problem? And if not, why?
It is not gas dynamics. If you see for the power plants, in a power plant, if you
Hmm.
see the cooling fluid changes the phase also.
Interesting. Yes.
Yeah,
But why? But then why? What is that factor that is uh, what is that factor that is not letting it be a gas dynamics problem? I'll ask you a
the
question.
Mach number,
The mark,
the velocities of
hmm,
the flow, the
the
velocities of the
velocities of
flow
the
are
velocity.
uh,
Interesting. But my question is, then it means, uh, then this means that my energy and momentum equations are coupled, and still the regime is non-gas dynamics,
yes, yes,
right? But again,
yes.
uh, great. Again, fine. So now we also understand the fact that it is not true that energy and momentum equation, if there is a coupling between these two equations, it will always be gas dynamics, right? But if it is gas dynamics, it will always be the coupling is gonna be there. The energy
Yeah,
equation, the temperatures are gonna affect the pressures, the velocities. Pressure and velocities are gonna affect temperatures, and there will be a vice versa relationship. In a heat exchanger problem, that that is the case. The temperature affects the velocities. But you know what? The pressures do not affect the temperatures. There is only one-way coupling. There is no two-way
okay.
coupling.
Hmm.
And he precisely mentioned the fact that velocities of the flow is what describes the dynamics, the regime of gas dynamics. If in heat exchangers, the flows are very slow compared to the speed of sound. And in a heat exchanger problem, the flow is still incompressible. See, when I started, I was very confused when I first saw this problem. My densities were changing, but it was still, I could still treat it as incompressible. How is that possible? Densities are changing, but the flow is still incompressible. That is what I'm saying. In a heat exchanger problem, in a heat exchanger
Yes,
problem, the flow remains incompressible instead of density changes. How is that possible? Does someone know
Gayan,
what is the mistake I'm making?
mm,
Sir, Mach number less than 0.3.
Yeah, but Got it. Got it. I'm saying density is changing, but the flow is still incompressible. How is that possible? Precisely the point I'm trying to make here. How much time have we gone through? Okay. Okay. Precisely, you see, incompressible, what does incompressible flow mean? There is incompressible fluid. Okay. Incompressible fluid will never change its density, no matter what you do. You take compressed water, it will not, no matter what you do. Okay. If you have taken truly incompressible fluid, water itself is a compressible fluid. It's not infinite, like it's not a perfect incompressible fluid, right? That is why water also changes density. But if you take a truly incompressible fluid, it's not going to change density. That is one thing. The second thing is, even if density is changing, the flow is not incompressible. That is something very peculiar. That is the essence of gas dynamics. That is very important. The thing is that the density changes are not affecting pressure changes. Okay.
Okay.
When I
Okay.
when do you get my point? Pressure remains constant in
Yes.
a steam power plant, right? Density
Yeah.
is changing. Agreed. Density is changing. Why? Because of thermal expansion. Density is changing because your temperature is increasing. Again, energy equation is coming into the picture. Energy equation and also one more equation. This equation of state. Density will change because of temperature change. Only because of, not because of energy equation. Because of this equation of state. This temperature is going to change because of energy equation. But in incompressible flows, pressure is not going to change because of density changes. That is very important. So let me point that out, and let me see if I can um, uh, write that down. Is there a statement that I can write down which emphasizes this fact? Let me think about it.
Com compressibility factor itself.
Compressibility factor. See, compressibility factor is a property. It's a fluid property. It's not a
Yes,
flow
yes.
property. It's not
It
a,
relates the pressure and the density only.
agreed. But that is what
Yes.
a fluid property cannot decide. A fluid property will not decide if the flow is compressible or not. Fluid properties do not decide if it's you are correct when you say it's the velocities. Velocities do decide it. But I wanted to emphasize,
Okay.
you get my point. See, water will have
Yes,
some
yes.
finite compressibility, but it is still incompressible flow if there is no phase change, if there is simple things going on, right?
Yes.
You can't have compressible flow unless there are large pressure variations. For compressive flows, you have large pressure variations. Why do these pressure variations comes? Because there's a heavy coupling between energy equation and momentum equation. The densities are changing, um, the densities are changing, the velocities are changing, and the temperature will also change. Yes, you see, pressure. There are, see, the conservation equations. Suppose continuity equation is velocity. Suppose just assume that uh, conservation equation gives you velocity. This continuity equation, momentum equation gives you pressure. Assume, and energy equation gives you temperature. All these three variables are related with by the fourth equation, which is the equation of state. Okay, so there is a heavy coupling between all these four equations uh, in gas dynamic flows. Okay, I'll think about how to emphasize the fact which I mentioned, that uh, even if there are finite density changes. I remember. I remember. Yeah, that is what I was thinking. If you can write this down. Then this is incompressible flow for sure. If density is not changing with pressure, then or let me say, let me, well, this is not correct. Let me say is so this is what I'm trying to say. If this is the case, then the flow is incompressible flow. If you can't neglect the pressure dependence, if you can't neglect the pressure dependence of the density, then this is compressible flow. And we can show this that this dependence is only important when you have large velocities. So how can we see that right now? Let me see. So I'll write the three equations just out of memory. I don't know if I will be able to get something positive out of it, but let me see. So this is the energy equation. This is rho u, not rho u square. This is rho u. This is rho u square plus p. You know what is this equation called? The second one, the momentum equation. What do you call this equation?
Euler equation.
Ah, interesting. But to be more precise, this is the steady Euler equation. And also this is
Yes, sir.
one dimensional steady Euler equation. Euler equation is a more general thing. You have to write it in partial derivatives and all. Finally, I'll write this. So, Adarsh, did you understand the discussion we had? Jayaprakash and me. Do you agree with it? Do you disagree? Is it confusing? Any feedback you want to give?
No, sir, clear.
Clear, full clear. Nothing. No,
Uh,
nothing is wrong.
Clear.
Interesting. Interesting. Oh, very interesting. Good. And finally, I'll write energy equation. I'll write it like this. Okay. H. Let me write it as H. So right now, to be very precise, that is why I'm replacing T with H. Okay. Okay. Now, how do we see that if this is true, velocities are high enough? Okay, we want to see this. Let's do it counterintuitively. Let's see. Let's do it by what do you call it? By disproving this. Let's see. So if you are able to see my screen, right? If rho is a function of, let's assume that rho is a function of only p. I don't know if I'll get a good answer to this because I'm doing all this by memory. So please forgive me for all this unstructured discussion that we are having. Okay. If let's assume rho is a function of p, rho does not depend on h. Okay. Then what happens? Uh, then you can write p is a function of constant minus rho u square, right? Someone is trying to enter the lobby. Just give me a second. Okay, p is constant minus rho u square. Then what else? Guys, do you see any proof? Can you prove that if rho is a function of p, then velocities will be very small? Then velocities will be very small. That is what we want to see. We want to prove that if u is tending to 0, then rho will only be a function of p. Okay, this is one way of to see. Okay, um, h will be constant plus u square by 2. This is okay. This is one more thing. When I wrote this equation, this is a adiabatic energy equation. Okay, let me add this q term here. Let me add some energy that we are adding. Okay, uh, this will be E or E dot. Let me think. This will be E or amount of energy that we have added. Guys, you're following me, right? Anybody having difficulty in
Yes,
what
sir.
I'm trying to do?
Yes, sir.
So, so this can be 0 for a adiabatic flow. No heat transfer is going place, but I'll assume that there is a heat transfer. Okay, because I wanted to show that in presence of heat transfer also, you can imply that this is gonna be true. Okay, so we'll take some E naught. this constant will, so you get this, right? You E0 plus Q, this you get, right? How will we get this? This is the constant. If Q was 0, this would be a constant, right? Some H plus U square by 2. I'm saying some additional energy is being added, and so this is the enthalpy that you're gonna get. Uh, then um, then what? Um, and then one more thing. Rho is some constant, some K by U. Okay, so we will have what? Okay. Ah, now we can see it loosely. Now I can very loosely we will be able to see this. To be more precise, we have to do some. I will have to uh, frame the proof properly right now because we are doing loosely. We are talking, so I'll show it to you how you can get it. See, you can see if I substitute U here, I'll see that rho is a function of H, right? Does someone see that? And that will negate the assumption that we had taken. Actually, this is some assumption that we had taken, right? Only if U is 0, uh, can H be not dependent on U. That is what I'm trying to say. This is a very uh, actually the proof. This is a very personal proof. Okay, this you are not gonna find in any book, and also this proof is not also correct. Also, this statement, although this statement is correct, but this statement you won't find in some book. I can show it to you in some book I have found, but again, this is not very famous statement of compressible flows. Let me be precise. Let me be very clear to you. This is something. This is coming from personal experience. But I think if you can cross verify this, if you can disprove this, can you disprove this? Does someone think that this is wrong? Then please let me know. I don't think so if this is wrong, but this is precisely what incompressible flow and stuff is, because that is why I motivated this equation also. See, in a heat transfer problem, enthalpy is changing, but it is not a gas dynamics flow. It's not a compressible flow. Why? Enthalpy is changing, density is changing, but pressure does not change. So it has to be related with pressure, first of all. There has to be large pressure differences. But if there is a large pressure difference, does that make it a gas dynamic flow? If I have a very long pipe, does that make it a gas dynamic flow? No. It has to do with the coupling and stuff, which we talked about. So overall this is true. And with the famous definitions, famous introductions we have for gas dynamics, you can show this also. But this will require you a a very detailed proof and stuff, which you don't require. That is why this is not introduced in the first class. This is not required when you introduce this concept of compressible flows. This is never introduced. Okay, I introduced it to just point out some intricacies in gas dynamics flows. This happens. This is an important aspect of it, just to give you an overview. Okay, just now let's complete this proof so that we'll close it then. Okay, what is the point here? Uh, yeah, so point is, see, if rho is a function, because we know conservation of momentum says that rho has to be a function of u, and u itself is a function of h. If this is true, if u is comparable to h, only then okay, this also we can see. see see if um, see if h is of the order of u square by 2. Okay, then you can definitely be sure of that. You know that we do this in in this also. Fluid mechanics also we neglect terms by order of magnitude analysis. We say that in boundary layer we also do that. This term is not important. Let's neglect it. Right? We do this,
Yes,
right?
sir.
We do it a lot of times. You see here, if I'm saying these two terms are comparable, that is what we do, right? In Navier-Stokes and boundary layer also, we say that this term is comparable to this term, right? The viscous term is important to inertial term and so on. That is how Reynolds number come into the picture. So I'm saying, and this is how, see, you'll see Eckert number is gonna come very soon now. Eckert number is gonna enter this picture very soon. But I'll not do it. I'll not show it to you because Eckert number is again a big deviation from the course itself. But you see, if they are comparable, then rho is it for sure not a function of alone p. Rho will have to be a function of h. You see that, right? Guys, anyone?
Yes, sir.
Right? Now assume that these terms are the important terms and these are much, this one is much, this one is a much smaller order of magnitude. Smaller order of magnitude compared to this. Suppose h square by 2h is much smaller than 1. Okay. Then, essentially speaking, if there are so small changes in u, h will largely remain constant and will only be affected by q. If q is 0, h will remain 0. If q is some value, h will increase on that order of magnitude, whatever and energy, whatever heat you are transferring to this fluid, it's gonna change on those order. But if u square by 2 is much smaller than h, then h will largely be constant, right? It can never be in
Yes, sir.
exactly this thing. It can never be exactly incompressible flow. That is what I told you. It can be exactly incompressible if the governing ideal this equation of state itself says that rho is not a function of a p. Wait, something is wrong. Sorry, I got disconnected. Is it? See, to be um, exactly speaking, only a incompressible equation of state. Hello, am I audible?
Yes, sir. Audible.
Yes, yes.
Yeah, sorry for this this break. I'm saying if we go into exactness, if we say that exactly, can you show that if this thing is there, the fluid will only be incompressible if u is 0. You can see that, right? If u is 0, only then you can write this thing down. Sorry, I've written it incorrectly. This is the thing. I've written this thing incorrectly. Okay. Okay. If rho is only a function of h, okay, let me write it down fully. Then we can say the flow is incompressible. I've written it down. No, that's fine. Incompressible. This I've written down here. I got confused. Um, this I've written down. No, it should not be a function of pressure. Okay. See, h is a function of u and p is also a function of u, right? So you will see that you cannot neglect this p because h is all u is coupling h and p. If u is a very uh, uh, u is a very comparable, like u is a very strong term, u square by 2 is a strong term, then h and u will dictate a coupling between p and h because energy, this equation of state is always this. Equation of state is not is never gonna be not dependent on this. This is the equation of state. But if we can approximate this, just give me a second. What is wrong with this? Anyways, if we can approximate, if let me write this down. If we can approximate rho is a function of h as rho is a function of h, then only the flow is incompressible. Then we are not dealing with we are not dealing with compressible flows. That can only happen if u is a small function of u is a small function of h. Let me see. Am I making sense? Yeah, because then there is no coupling between these two equations. If u is not affecting h largely, and u will not also affect p largely, right? You might want to say that then this thing should be there. Then something of this thing should be there. We should write something of this sort, right? For incompressible flow. I think I'm not making much sense at this point. This thing has become too complex. So I'll do this properly again next time. Let me think if I can simply, if we can close this broadly. Let me think. If we can do, if I can show that Mach number is gonna enter now very soon. So see Mach number, this is, see H if I write Cp delta T. Okay, CPT. Let's write CPT right now. Okay, and then CP is some gamma. What is it? CP is
Gamma
some R,
minus one.
right? CP some R. CP is some R, right? RT. So you see gamma,
R by gamma minus one.
right? Gamma, yeah, R gamma into gamma minus 1. So yeah, that's correct. Let me write that down. Gamma into gamma minus 1 or something of that sort is gonna come. And you see Mach number is gonna enter very soon. You see that, right? Because this will become velocity, this will become speed of sound, and you will have the square of Mach number is gonna be much less than 1. Okay. If so basically something which what we are gonna get is Mach number square is much less than 1. Okay. I'll show you how 0.3 comes. If Mach number, if I remember it now. This now I remember, but again very loosely. Whatever I was trying to explain here, I'll show it to you how that comes. Maybe next time because I don't remember it completely. But it comes from these three equations only, and they actually don't consider this term. They consider Q to be 0 in that proof. So let me think.
Sir, in isoentropy flows, the total stagnation enthalpy remain constant. That
Yeah,
static.
this is the stagnant enthalpy. But stagnant enthalpy is also not constant in heat transfer conditions, in heat transfer flows. Stagnation enthalpy changes in heat transfer flows. That I wanted to do it as a general proof. I didn't want to um, just introduce. See, that proof is correct to just introduce it, but generally speaking, it's not a general proof because in heat transfer flows and stagnation enthalpy is not constant. Okay. Anyways, that proof is available. That enthalpy, this if density
That is
changes are
for
much
gas
less than.
dynamics.
Yeah. It's no, gas dynamics can have heat transfer also. So let me just complete the statement I was trying to make. That this statement, the density changes are less than less than 5%, will impose that Mach number is less than 0.3 is gonna come from this proof only. Simpler proof, not exactly this one. And right now I'm not able to, let me see if I can show it to you. See, if u is a very small fraction of h, then you see that they become decoupled. These two equation becomes decoupled. Can you see that? If u is much smaller than h, because h will not largely be affected by u, and so will p. Because see, I've written this equation as like this. Let me write this equation as little differently. Again, this is a manipulation. Whatever I'm trying to prove, right, is to just give you a feel. That is why it might seem that it's not precise, but forgive me for that. We can write the equation of state like this as well, right? You see, if u is very small, h is not gonna change, and p and u are dependent by this relation. So you can say, what else you can say? You can say that. Uh, you would be able to say that pressure will not change with the with pressure can simply be a function of h, I guess. It will not be a function of rho. It will not depend on density. That is what I wanted to say. You can't, that won't happen. So not equal to in incompressible flow, or rho is not a function of P. This coupling between density and pressure just goes away. Okay, that is what I wanted to emphasize. Let me write this down. I know I'm not making sense. I'll make this clearer in the next session, because I came unprepared. I'm not able to complete this proof. But that is the essence of gas dynamics, that the coupling between density and pressure is largely related with equation of state and also the energy equation. And this coupling breaks off if the flow is incompressible. So a lot of things, it's a little complicated, but for introduction, we can discuss these definitions, that density changes are smaller than 5%, and that is going to happen at high Mach number, only at low Mach number flows. So that proof, I think, um, let me see if I can give you that proof. That proof is there actually. Let me see. It's in Kundu also. Let me share the screen. Let's see if we can find that proof. Okay. Let's see how a book, textbook, introduces this gas dynamics as a concept. Okay. This is a book on fluid mechanics. So again, not a specific book on gas dynamics. So let me see. It will give a good refresher to what gas dynamics is. Okay. Right. So it gives you this. It straight away goes ahead and mentions Mach number, and it mentions speed of sound as a formula of pressure. See, yeah, this is what I was not able to show. So this comes from thermodynamics, that speed of sound has a relation with the gradient between pressure and density at constant entropy. Okay, just hear me out. Don't get don't get bogged into details. Just hear me out. I'll do it more precisely next time. Okay. Now, if you write the mass conservation equation and substitute momentum equation to it, you will get this expression. Okay, you see Mach number is entering the picture. Uh, in that case, if what else is there? Let me see. It's gonna come from this equation only, I remember. Yeah, if let me see. You see this. Yeah, the subscript signifies the partial taken in direction scaling, compressible flow is there. You see this. See, this is the incompressible condition, right? If the flow is incompressible or not. This is the changes in pressure with respect non-dimensional pressure change. You see, Mach number decides how these two are related. This goes zero for incompressible flows, right? Truly incompressible flow, this will be zero. In Mach number tending to zero, the flow will be zero. I'll do it properly. I don't think I am making much of sense. So let me see where rho naught are approximately this thing. Pressure is scaled by fluid inertia. In engineering purchasing assumption presumed if 4.110 suggests that Mach number 10% departure for perfectly. How does that see? This is the equation where you get that 5% and 0.3 relation. Let me just see. We get that? I've forgotten it. So what does it say? Let's read. The Here, the subscript s in this equation, the subscript x signifies the partial derivative taken at constant entropy. In particular, the dimensionless scaling of the compressible flow continuity equation. So this is the compressible flow continuity equation for isentropic conditions leads to this formula. Okay, where rho naught and p naught are appropriately chosen reference values for density and pressure. Pressure is scaled with fluid inertia parameters. So rho u naught square. This is the fluid inertia parameter. It is scaled by P is scaled by rho u naught square. In engineering practice, the incompressible flow assumption is presumed if Mach number is less than 3, but not at higher Mach numbers. Equation 4.110 suggests that Mach 0.03 corresponds to 10% departure. So it's 10% departure. For 5%, it's even lower, I guess. Okay. So let me see. From how do we get this? Can someone tell me how will we get that fact that if density departure is actually you can write it as d rho by dt, I guess. What you can this term. Well, I don't know. I've forgotten
The
this.
gradient of velocity function equal to Mach number. That is a p minus p naught static minus stagnant pressure divided by denominator part is the dynamic pressure.
No. This is not stagnation pressure. This is a reference pressure. See, reference values. These are not stagnation pressures.
Reference means static.
No. Reference means static only. Right now, static only. There's no stagnation right now.
At any
You can,
arbitrary point, we can consider.
yeah, yeah. This part I'll discuss with you next time. Okay. Now let me just conclude. This part, I'm getting confused a little bit on how do we get this. Let me just one last time see. Yeah, I'm not sure. Maybe something we are missing. That is why we are not able to do it. I'll see. Okay. So so basically, today I came unprepared. Sorry for that. Let me. Yeah. So a couple of things before going. Before leaving. First of all, we took a lot of time today. It's almost 20 minutes past the dedicated time. That will not gonna happen. That is not gonna happen. I'm gonna start at sharp 6 and at sharp 8 every time from the next week. I was not prepared today, so sorry about that. Uh, the sessions are not gonna go like this. I'm not going to be spontaneously discussing things. The discussion we had today was a little bit jagged, so excuse that. We are going to have some good flow in the paper in that discussion. And one last thing, we are going to discuss this. We are going to complete this discussion. I'm missing few things. I'll come back and discuss this with you one last time. Okay, next time. So if anyone has some questions, if anyone has some expectations from the class, you can go ahead and also tell me that so that I can prepare the sessions accordingly. Also, I'm not
Sir,
hmm.
Sir, in our university, one of our faculty members said compressible flow by E. Radhakrishnan also.
Sorry, Adarsh, I'm not able to properly hear you out. Can you type your comment in the chat bot? Sorry, it's very you can unmute your.
In our university, one of our faculty members said at the time he referred the book called Compressible Flow by E. Radhakrishnan. Also, the third.
Yeah, just type whatever you're saying in the chat bot. Just one last thing. Another just comment. I'm not a big believer of internet is not there, is it? No, it's fine. The thing I was saying was I'm not a big fan of this solving very simple problems. Okay, solving some formula putting things. So I will try to avoid that because that helps no one. Me solving a very stupid problem, putting in formulas is not a good idea. We'll try to keep it concept oriented. The problems that all the problems that we are gonna do. I'm trying to. This is my my premise, which I am coming from, I'll try to do that. Okay. So please let me know if there's a problem with that. What are your expectations from this interactions? We can discuss that too. If you have any questions, you can go ahead. Otherwise, if you are okay with, if you're done, you can start leaving the meeting also. I'm here for answering any questions. So yeah, great. What is going on? What is this? Hmm. So he's mentioning the books. Adarsh is mentioning some books. Sir, one of our faculty told that he referred at his time. He, Radha Krishna. Let me see. This is a different book, right? Gasdynamics by E. Radhakrishna. It's okay. As long as you understand the concepts discussed in the video lectures, any book is fine. There is no, see, the assignments are already there. So no, you type in. I think there is a lot of disturbance. So I'm not sure. Right now it's a lot of disturbance there. So you can just type in. We can talk on chat also. There's no problem. You can just type in your message. I'm here. Other guys can leave. I am here. Don't worry. I'm saying you can, as long as you can understand whatever is being taught in the video lectures. That is okay. That is fine. See, assignments are already coded in the NPTEL courses, so it's not like which book will help you from the exam point of view. That I am not. I also am not sure, because those questions are um, like selected by professor. So any book whichever serves your purpose is okay. Don't get bogged down by the books and references. That is not the intent. Okay, the intent should be to understand this concept. I realize that even while teaching you this stuff, this density and pressure decoupling, I also got a little confused. I couldn't tell you properly, clarify it. So again, my understanding is also not very good when we go into the details. But it is at the end of the day derivations, which we are not to forget. So that is also okay. So fine. So that is nothing to worry about the this references. You can refer to it any. Yeah, yeah. If Srisha Rao sir suggests this book, go ahead. Go ahead. No problem. Then the best only. You go ahead. But I am gonna follow my own thing. My own thing, I mean the questions we are going to discuss. You can bring your own questions, the questions you would like me to solve. I can do that. But I don't know if I should follow some books suggested by someone. I'll follow my own books, I guess. Is that okay? Yeah, so let me type this down for him. He's great. So it's all fine. I think others, then we're done, right?
Yes, sir.
Oh, we're not recording, is it? Oh, we are recording. Yeah, so I will log out. Um, uh, we already did a 2 hour session today, so not going to put up another session. This one was much
Sir,
like this was.
what is the
Hmm.
time? What is the time for next session?
What is the time for?
Next session.
6 to 8. 6 to 8. 6 to 8.
Acha,
You
Monday.
follow the time on the 6 to 8. 6 to 8. Okay. Okay. So I'll log out. Fine. So bye guys.
In
See you
Thursday,
soon.
sir. Thursday.
What
Thursday, 6
percentages
to 8.
for?
Okay.
I think Tuesday is 6 to 8.
Sorry, Tuesday. Huh?
I think Tuesday is 6 to 8. Okay.
Okay, sir. Good night.
Okay, guys. I'm logging out. Good night, guys. Have a
Good night.
beautiful weekend ahead. Bye.
Yes, sir.